Okay, so let's start with something which I think eventually is going to be the way to go. Conical flow, 3D flow. Okay, as you've seen so far that the equations involved in solving various sorts of problems are complicated, are large, numerically exhaustive. So we'll sort of go step by step. Okay, so one of the reasons of doing like 2D flow, because it cuts down the really the number of equations or the largeness of the equation. So if I do this, so the simplification of the numerical procedure is something which is sort of paramount when we do 2D flow. Otherwise, we would have sort of just gone into 3D flow and done that. Okay, so when I say 3D flow, let's sort of go slow with this and try and understand what I'm trying to say. So let's say today's lecture is about conical flow. Okay, now what do I mean by that? Okay, let's say let's draw an axis system. Let's call that as okay. Okay, so now basically what you can see is this is the cylindrical coordinate system, right? So we have this. Okay, this is a radial axis, a z-axis, and a phi. So now therefore here, okay, so if I have a body like this, okay, okay, now that's my cone. So that's my conical body, and we have a free stream coming in. Okay, so this is something that we're talking about. So a flow which would go past a body like this. Now let us sort of list out some of the properties of this sort of a flow that you're going to look at, and then go ahead and look at the equation that we need to solve for it. Okay, so okay, so like you said, this is a 3D flow. Okay, we will really looking at 3D flow, and the body, if you look at this, is essentially it's a planar curve, right, and which is rotated about a fixed axis, which is z here. Okay, so in this case, okay, as you can see that z is basically the sort of goes through the middle of the body, or which sort of is symmetric. The body is symmetric about the z-axis, or you can say z-axis is the line of symmetry of the body, and the free stream velocity direction is in the direction of the is basically is in the same as the line of symmetry. Okay, so therefore in here what I say, the angle of attack is 0 degrees. So essentially what I'm trying to say here is that if I take this as the line of symmetry, if I take this as the line of symmetry, then this is making 0 angle of attack, a 0 angle with this free stream, and hence I write as angle of attack is 0. Right? Then, of course, this is a cylindrical coordinate system that we're looking at. Okay, we're looking at a cylindrical coordinate system. yes, and like I said, z axis is the axis of symmetry, right, and v infinity is aligned to z. So essentially what happens here is that the flow is symmetric in the phi direction, right. The flow is symmetric in the phi direction. So therefore rather flow, yes, it's in line. So the flow is basically symmetric about the z axis, right. So essentially the flow is not varying in the direction of phi. So which essentially, because this essentially means that, right. So properties which are properties are not varying in the direction of phi. Okay. Okay, so now having said that, so since we said that the angle of attack is 0, flow is symmetric about the z axis. Okay, so the flow here is 3D flow. Okay, the flow here is 3D flow, but then we really have two independent coordinates. Okay, so essentially what we have here is it is a 3D flow. We have two independent axis. We have two independent axes, right, which is okay. So which is basically the radial and the z directions. Okay. Now such a flow, okay, it is the 3D flow in space with two independent axes, because we have a free stream which is in line with the axis of symmetry, which in this case is the z axis, okay, which means that the angle of attack is 0. Okay, and what this makes it is therefore axisymmetric. What that means is that this is an axisymmetric flow, right? It is an axisymmetric flow, which also essentially means that it's a quasi 2D flow, right? It's a quasi 2D flow. So this is a kind of this is the kind of problem that we're going to look at now. Okay, and hopefully within another couple of lectures we should really do a full solution. Okay, we should look at the solution of a full 3D problem which is not axisymmetric, okay, where these two are not in line and the angle of attack is not 0. Okay, we'll come to that. So let us start with something like this. Okay, now this also is so basically what we're looking at is the problem here is supersonic axisymmetric flow, which means this, right? Now let us also look at some of the things here. So why is this problem important? Now why is this problem important? Well, number one, so we is comparative ease with which we can solve the exact equations. We are not going to use any sort of linearization for this sort of thing. This has a lot of practical applications. Okay, well, historical significance. Now the first solution to a problem like this was given by Boozman in 1929 actually. Okay, there is this guy called he suggested a solution for this, and then finally in 1933, Taylor and McCall basically, so G.I. Taylor and McCall, they gave the very significant solution for supersonic 3D axisymmetric flow, and that's what we are going to look at right now. Okay, we're going to look at solution and how we go about this. Okay, such a problem. So now every time you see a supersonic sharp-nosed vehicle, you can always think of a solution. You can always, and you're thinking, oh God, how did they make this, and how do they decide upon the shape? Well, let's see if we can find some answers to that, because this is a kind of analysis which basically has applications for, supersonic flow, nozzles, and sharp-nosed vehicles, and so on and so forth. Okay. All right. So let's get some diagrams in place. Okay. Now, first things first, let's look at this. So essentially what we're saying is this. Right, if I have a Cartesian coordinate system, okay, if I have a Cartesian coordinate system, okay, so I mean basically what I'm trying to do here is look at this cone. Okay, if we have this 3D cone, how does it look in the space that we're most comfortable with? So if I have this here, and say I have okay, so I have so basically this is my cone. So this is my Cartesian coordinate system, and this is the picture that I'm looking at. Okay, so now what we'll do is we will look at the coordinate system that I'm talking about. Okay. Okay, got a nice yellow chalk here. Okay, so now, okay, let us use this. Okay, so this is essentially a radial axis. Okay, and if you drop a perpendicular onto this plane, right, onto this plane, then you essentially get that. Okay, now let us look at some angles. So if I have this, now this is essentially making an angle phi, okay, and this r is making an angle theta. Okay, so this angle is making an angle theta. So therefore, now if you look at this, so as you look at this, so in my x, y, and z coordinate system, this is the cone, right? Then this radial line, so now if you basically look at this radial line, if you take the x and z coordinate system, right, you take a line and rotate about, say, this point, and fix it at this particular point, take this radial vector, okay, and fix it at here, and then rotate it about the z axis. What you will get is this curve, which is this 3D volume here, which is the cone, right? So if you take that and you move it this way, then you are able to generate this particular curve. So therefore, this is a radial vector. You drop a perpendicular of that into the xy plane, so that makes an angle y. Okay, this makes an angle y this makes an angle phi with the direction y. Okay, so and this is essentially the direction of the free stream. So, this is the direction of the free stream. So, this is basically, so this is the geometrical system that we are looking at. Okay? This is the picture. Now, so let us go back now, see the similarity of this picture. So, same thing. Now, if I do this, this is again my x axis, right. Now, I am going to just look at, so what I am looking at is r, okay, phi and z. So, this is the only thing that I am looking at. Okay. So, x here. So, therefore, in this axis system, so therefore, I have okay. So, if we have that, okay, so then okay, so let us draw this here. Okay. This is a this is my radial, this is my radial vector. Let's draw that a little less smaller. Okay. Oh. Okay, so let's draw that a little smaller. So, we have this r, okay, and of course, if you have a so you have the velocity free stream coming in from here, right. So, therefore, that would make what we have been doing so far. Right. So, this is my shock wave. So, this is my shock. Okay. So, now let us look at this. Now, what angles are we talking about here? So, what we get is, so let us call this, okay, as theta c. Okay. This I am looking at the physical picture here, which is theta for the cone, say. Okay. And this, of course, is theta of the shock angle. This is this theta of the shock angle. Okay. And yes, so r is basically so this r, so this essentially makes an angle theta everywhere. Okay. So, now if I were to define say a unit velocity vector, okay, unit velocity vector. So, let us say I do that. Okay. So, if I have a velocity vector, so the radial direction velocity vector is v r, and in this direction is in the theta direction is v theta, perpendicular to the r direction. So, this is the kind of geometry we are looking at. So, like we said before, yeah, del phi is equal to 0. So, any derivatives there are none actually, because it is axisymmetric. So, properties do not change in phi. So, this is 0. Okay. So, also now in this particular, if you look at this diagram, now if you have properties in here, properties are also constant along a radial direction, right. It is also constant along a radial direction. So, therefore, so let us write this, properties are constant right, which means that okay, right. Now, armed with that, okay, let us begin to look at the equations. Now that we've kind of sort of looked at some of the pictures here, trying to understand the geometry a little bit, let us go and look at some of the equations. Okay, so let us look at this, the continuity equation for a steady flow. So the continuity equation for a steady flow okay. So now let us do that and then write this in spherical coordinate system. So if I write this, okay, now don't get scared by this, okay. So what we get equations, if I break this up and write this down in the spherical coordinate system, how will this look like? So let us look at this. So you can find this in any book. I'm going to write this so that we can look at it here and see what we're going to do with it. Okay. So you can see the terms appearing here. Okay. Okay. So now if I write this, okay, in this direction. Now let us look at this particular equation over here. If I look at this particular equation here, as we've just said that the properties remain. If I look at this particular equation, the properties in the radial direction remains constant. So therefore, derivatives, there are no derivatives. Okay, so therefore del r goes to 0. So this here actually goes to 0, and also okay. So so this is essentially because properties along r direction constant. Okay. So now again, this is an axisymmetric problem. So it is symmetric about the z axis. So therefore, it does not vary in the phi direction. So again, this goes to 0, right? And this is because so this sort of goes to, should we write it this way? Yeah. So okay, if I have this, okay. Now before I do that, okay, let us do a thing. Let us go and expand this, okay, and then we will apply this. Okay, let us go and expand this, okay, because we might miss out on a term or two if I do that. So if I do this, if I'm going to expand this, okay, what I get is this. Okay, so let us sort of expand this here. So what we get is r square okay, 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 that plus the second term is 1 by r sine theta, which is rho phi theta cos theta plus sin theta tan theta. Okay, and we'll leave that as it is. Okay, so this one is of course axisymmetric. So this is axisymmetric. Okay. Okay, and this term, you see, if I expand it, so I get this. right? If I get this, you see I would have lost out on this term if I put that in here. So now we'll go ahead and say that this is 0 because properties along r are constant. So let's say the properties in r direction are constant. So therefore, we go ahead, we get rid of this. So ultimately, so the equation that we come up with, therefore, if I look at this, so I have 1, 2 and 3 terms here. Okay. So if I look at this, what I get is this. Okay. So this, and then I can just multiply it by, you know, r through r, and what I get is okay. So if I differentiate this as well, so what I get is right. So this is the equation. This is from the continuity equation that we're going to try and use. So let's call this here. So this is what we get from the continuity equation for axisymmetric supersonic flow. Okay. So we get this particular equation. Now, if you remember the Crocus theorem, which was giving us a connection between the thermodynamic properties and the kinetics of the flow. Okay. So if you remember right, okay, or let me sort of write it out again and remind you. Okay. So let us go here. Okay. Okay. So if you remember this, this was our Crocus theorem. Okay. So which was okay. So essentially the momentum and energy equations combined. So we got, this is the Crocus theorem, right? So it connects the thermodynamic properties with the kinetics of the flow, right? Now we know for this here, so the flow out here is isentropic. Okay, the flow out here is isentropic. Okay, which implies what? Okay, and it is adiabatic and steady. Okay, we consider adiabatic and steady, which implies that enthalpy is constant, right? So this is what it implies. So if I look at this equation from here, so essentially what I have is both these terms go to 0, which means that this too is equal to 0, right? So therefore, if I have for a supersonic axisymmetric flow, which is isentropic, adiabatic and steady, then this holds, which is, as you can see, this is an expression for the irrotationality of the flow. So, and a supersonic axisymmetric flow, which is isentropic, adiabatic and steady, is also irrotational. Okay. Now let us see what this means in terms of our velocity components, Vr, v theta, and so on and so forth. Okay. So, del cross V is this. Okay. And okay, so in this direction basically you have del R, you have del theta, del phi, you have phi r, phi theta, r sine theta, v phi, and what we just found out that this is also equal to 0. This is also equal to 0. So, what do we get out of here? Okay. So, if I'm going to go ahead and expand this. So, what I get from there is this. Okay. What I get from here is this. Okay. 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 Right. So, if I expand this whole thing, what I get is this. You can cross check this. Okay. You can just cross check that. Let me just do this for you. So, ER. So, ER basically I do this here. So, del theta of r sine theta v phi. So, which is this minus del phi of r v theta. That is what we get. Then minus ER that into these two, and this here, this is the, so del r of r sine theta v phi minus del phi of VR, and so on and so forth. R is this out here. So, r sine theta into E phi is del r of r v theta minus del theta of VR. So, that is it. This is what we get from here, right, and v theta, but there is really no v phi, okay, because it is axisymmetric. So, the v phi term is not going to be here. So, we do not have any v phi. So, let us sort of, this goes to 0 and that goes to 0. Del phi is axisymmetric, so that goes to 0. Del phi axisymmetric, so that goes to 0. So, you can see what we are left out with. We are just left out with r and theta over here. So, what we get is this del r of r v theta. So, del r of r v theta minus del theta of VR is equal to 0. That is what we get. Let us expand this first one. So, what we get is v theta plus r del v theta del r. Okay. Okay. Now, again in the radial direction properties are constant. So, therefore, this also goes to 0. So, what we essentially get over here is that v theta is equal to Now, this is interesting. Okay. So, in the theta direction, which is normal to the r direction, so all this we can call this as 2. Okay. So, all we basically do is take a derivative of the radial velocity in the theta direction. So, essentially what we are saying is that if we have a radial vector like that, right, a radial vector like the velocity like that, we are looking at the change of this radial velocity in the theta direction. When I change the theta like that, what is the change in the radial velocity vector? So, that is what this is essentially telling us. Okay. So, Euler's equations. Okay. So, on the I am not writing the body forces, then what we get is okay. So, this is irrotational. So, we have irrotational flow which has been right. So, what that means is that okay. So, if it is irrotational, I can write the change in pressure in terms of the velocity change and the density, right. So, if I do that, okay. So, now let us see how we will sort of write out the Euler's equation in terms of V r, V theta and so on and so forth. Okay. So, okay. So, let us just say here, so you know, V square out here, you know, let us say, okay. So, V square in here is V r square. Okay, that makes sense. So, the velocity here is the radial velocity and the radial velocity and the theta velocity direction. So, if I do that, okay, if I write that, so therefore, dP, okay, dP is equal to, if you look at this equation, okay. Okay. If I look at this, I can write in terms in the r and the theta direction, right. So, if I write this now, let us also recall that we know, okay, let us recall that, okay, let me use, okay, now let me go back here. Okay. So, now it is isentropic, right, it is isentropic. So, therefore, we also know that right. So, we know this from before. Okay. Now, having said that, so therefore, let us write this as okay. So, d rho into a square is equal to dP, and for dP let us put in this value in here. Okay. So, to do that, so basically what we get is that, which is minus rho into okay, this, or I can write this as, this equation. I can write as, this is d rho into a square is equal to this, right, or I can bring this here, right, making that as 1, okay, making that as 1, and take this a square down here. Okay. So, then this is what we get. So, d rho let us call this as 3. Okay. So, so we get this equation out here. Okay. Now, we said it is adiabatic. Okay. So, we said it is adiabatic. So, therefore, right. So, adiabatic, which means that enthalpy constant, right. So, if we do that, let us define another reference system in terms of the velocity, right. So, let us our new reference velocity. So, let us call that as a V max. Okay. Now, V max is essentially the velocity, is a maximum velocity, right, which is reached from the reservoir conditions, right, which is reached from the reservoir conditions, so that the temperature out here is 0, so that the enthalpy is 0, and this is the maximum velocity. Okay. So, which means that, so H naught, right, so which will be, right. So, the maximum, so H naught is nothing but this. Okay. So, I look at, and this is Cp into T into temperature, Cp into T, right. So, therefore, I reach the maximum velocity, the entire enthalpy is coming from the velocity and the temperature is 0. So, what we get here is, so this is my new reference, this is another new reference velocity. Okay. So, this is a velocity which essentially I am reaching by expanding the flow from reservoir conditions to a place where the temperature is 0. Okay. So, what you can see from here, therefore, what you can see is that V max is equal to 2 times the reservoir enthalpy, right. So, under root 2 times the reservoir enthalpy. Now, again, if I use for a calorically perfect gas, so let us just sort of rewrite this here. So, okay, so I am going to use this space. So, for a calorically perfect gas again, right. So, I can write this. So, in here, from here, what I will write is, what I will write here is this A square, right, which I can write as, and this I can write as V r square plus V theta square, right. So, if I write this, then what I get so I get a value for this A square. So, A square, now I take this A square, okay, and put it in this equation 3 out here. Okay. If I do that, let us see what we get. Okay. I take that value of A square, which we just got in terms of V max, okay, V r and V theta, and we will put it in here. Okay. So, what we get is, therefore, A square is okay, and we get and this V max square is nothing but 2 times the 2 times the reservoir enthalpy, right, which is a constant in here, because it is adiabatic, it does not change. So, if you look at this equation, if you have to solve it, maybe it does not sort of look that scary now. So, now this is essentially what I have reduced the Euler's equation to be. Okay. So, if I look at this, this is essentially okay. So, this is essentially my Euler's equation. Okay. So, we have just one independent variable. Which is theta, and we have three independent variables. We have three dependent variables, right, which are rho, Vr and V theta. Okay. So, therefore, what we can do is basically we can write these as simple derivatives. Okay. We can write these as simple derivatives. Okay. And I incorporate all of that into my Euler's equation, right, which I use over here. So, what I get here is something like this. Okay. 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 If basically all I am doing is combining all these equations. Okay. Okay, so that equation, so this equation out here, okay, let's call this as 5. Okay, so this equation out here is essentially the Taylor-Maccall equation that I talked about right at the beginning. So this is the Taylor-Maccall equation for axisymmetric conical flow. Okay, and this is the equation that we will try to solve, okay, for our axisymmetric conical flow. Okay, let's stop here. So, of course, this is there can be no there is no closed form solution for this. We have to solve this numerically. We will see how. Okay. So, essentially, so now at least we have got an equation which with which we can work with. Okay. So, we have made no linearizations, no assumptions, nothing. We have just gone from basic governing equations for conical flow and got this nice expression, and see how we can solve this for the kind of flow that we talked about, which is conical axisymmetric flow. Okay. Thanks.